This section is about Newton's second law, a very important section in physics. To explore this, consider a spring scale of the type used to weigh fish. So the scale gives a reading of the force F exerted by the spring contained within it. The first spring balance has no weight attached and the read is 0. Now if we hang one weight from the scale, it gives a reading that we call F1. If two identical weights are attached, the scale reads as indicated in here, F2 equals to F1. Therefore, with the two weights, the force exerted by the scale is twice the force exerted when only a single weight is attached. Now let's perform some force experiment to explore more about force. First, attach the scale to an air track cart as in this figure. So if we pull with the force F1, we observe that the car accelerates at the rate A1. A1 is the acceleration. Now if we pull with the force F2, which is equal to 2F1, 2 times F1, then the acceleration we observe is A2, which is equal to 2 times A1. Now therefore, the acceleration is proportional to the force. The greater the force, the greater the acceleration. So we can say that acceleration is proportional to force, or in symbolic form, A is proportional to force F. Now let's see how the mass is related to the force. So instead of doubling the force, let's double the mass M of the cart by connecting two together. So as in this figure. So in this case, we pull a mass 2M with the force F1, same as previously with the force F1, but now we find the acceleration to be equal to half times A1. Therefore, we can say that the acceleration is inversely proportional to the mass. So the greater the mass, the less the acceleration. And in symbolic form, we can write acceleration A is inversely proportional to mass M. Now we can combine those two results together. First we found that acceleration is proportional to the force, and then we found that acceleration is inversely proportional to mass. Therefore, by combining those two, we can say that A equals F over M, which is equal to F equals ma. So in general, there may be several forces acting on a given mass, and these forces may be in different directions. Therefore, we can replace the force F with the sum of the force vectors acting on a mass. Now, therefore, the equation becomes sigma F equals ma. Now, this we call as the Newton's second law of motion. Very important equation. So, net force is a vector and the acceleration is also a vector. And notice that the direction of an object's acceleration is same as the direction of the net force acting on it. Now we can write Newton's second law in terms of vector components, since force and acceleration are vectors. So in x direction, we can write sigma Fx is equal to mass times Ax. Here Ax means the acceleration in x direction and Fx is force in x direction, the net force. And similarly for y direction, we can write sigma Fy equals may. Fy is net force in y direction, ay is acceleration in y direction. And if there is another direction, the c component, we can write sigma Fvz equals to maz. Now the units of force is Newton. So F equals ma and m mass is kg, a equals ms minus 2, and then that is equal to Newton. So this table shows other common units of force. But please remember to use the SI units always when solving problems. Let's see one example that uses Newton's second law. So the net force acting on an airplane has a magnitude of 1900 newtons and points in positive x direction. So if the plane has a mass of 860 kilogram, what is the acceleration? And these are the known parameters. We are given the force, which is 1900 newton, and mass 860 kilogram. Only x component are involved in this system, so let's use the x component of the Newton's second law. So we are asked to find the acceleration. So it is sigma fx equal to mass times ax. Now we are asked to find the acceleration, which is ax. Ax should be equal to sigma fx over m. And now we can substitute the values. Fx is 1900 newton, mass is 860 kilograms. Both the units are in SI units, therefore acceleration is 2.2 meters per second square. Now we will be solving more problems using Newton's second law of motion. Now when we solve problems involving forces and Newton laws, it is essential to begin by making a sketch that indicates each and every external force acting on a given object. So this type of a sketch is often referred to as a free body diagram. Let's see the steps for constructing a free body diagram. First, identify and sketch all of the external forces acting on the object. Next, replace the object with a point particle of the same mass and apply each of the forces acting on the object to that point. Now choose a convenient coordinate system. Any coordinate system will work. However, if the object is moving in a known direction, it is often convenient to pick that direction for one of the coordinate axes. Now determine the component of each force in the free body diagram, and then analyze motion in each coordinate direction using the component form of Newton's second law. Now let's see an example of a free body diagram. A person is pushing a chair. So first of all, let's sketch all of the external forces acting on the object of interest. There are three forces, external forces acting on the chair when he is pushing the chair. The first one is the force exerted by the person, which is F, and then the gravity exerts a downward force, which is W, which is simply the weight of the chair. And now there is another force, that is the flow exerts an upward force on the chair that prevents it from falling toward the center of the earth, which we call as normal force N. We will be learning about normal force at the end of this lecture again. Now isolate the object and treat it as a point particle. So if we isolate the object and if we treat it as a point particle, then we can draw all the three components from that point, starting from that point. And then choose a convenient coordinate system. So the person is pushing in this direction, so it should move in this direction. So we choose x to be in this direction and y should be perpendicular to x. Now we can resolve each of the forces into components using the coordinate system we choose. So in two-dimensional motion, we learn about how to find the components of vectors. So the force is in this direction with an angle of theta, so we can find the x component f cos theta, and y component is f sin theta, but it is directed in the negative y direction, therefore it's negative f sin theta. And w is in the negative y direction and there's no x component. And for the normal force N, there's no x component and it is directed in the positive y direction. Now let's see another example of how to draw a free body diagram for a one-dimensional system. Suppose, for instance, that you hold a book at rest in your hand. Now what are the forces acting on this book? First we have to identify the forces acting on the object. Now two forces acts on the book. First one is the downward force due to gravity, W, which is equal to mg, and since the book is at rest, there should be another force acting on it, otherwise it should fall down. That is the upward force F exerted by your hand. Now we begin with a sketch of the physical situation as in this figure. Now the corresponding free body diagram shows just the book represented by a point and the forces acting on it, force and W downward. Now all these forces are vertical. So let's write down the y component of the forces. So sigma Fy is in y direction F minus W. If you select the upward is as the positive direction. Then we can apply Newton's second law, which is sigma Fy equals May in y direction. And the book is at rest, therefore acceleration is 0. So this part goes to 0. Therefore F minus W is equal to 0, and in this case F is equal to W. Downward force should be equal to the upward force. Now let's see another example. Consider a situation where the net force acting on an object is non-zero, meaning that its acceleration is also non-zero. So Moore, Larry and Curly push on a 752 kilogram board that floats next to a dog. They each exert an 80.5 Newton force parallel to the dog. Now we are asked to find the acceleration of the board if they push in the same direction. And in the part B, we are asked to find the magnitude and the direction of the board's acceleration if Larry and Curly push in the opposite direction to Moore's push. Now first of all, let's picture the problem and identify the forces acting on it. So in part A says all of them push the board in same direction. So there are three forces acting on the board. We can name them. Let's say the force due to Moore is Fm, and force from Larry is Fl, and the force by Curly is Fc. Now let's choose the positive x direction to the right, thinking that boat is moving in the x direction. Now let's draw the free body diagram for this case. For that, we consider the boat as a point object and draw these three forces in x direction. Now we are asked to find the acceleration. For that, we can use Newton's second law in the x direction, since all the forces acting on the object on the board are in positive x direction according to our sketch. Now in part B, it says two of them, Larry and Curly, push the board in opposite direction to Moore's push. Now we can first draw the physical picture for this situation as in part A. Here FL and FC are in negative x direction since they are pushing in opposite direction. Now if we draw the free body diagram for this case, again we consider the boat as a point object and draw these three vectors. Fm is in positive x direction and Fl and Fc is in the negative x direction. So again we can apply Newton's second law in x direction for this motion to find acceleration. If you are getting a negative value, then the acceleration is negative. That means it should move in the negative x direction. So let's do the calculation now. Now these are the known parameters. We know the mass, which is 752 kilogram, and force of each person, which is equal. And we are asked to find the acceleration in each case. Now in part A, we are applying Newton's second law, which is sigma Fx equal mass times Ax. We are applying in the x direction. And now what is the force? Sigma Fx. We have to add the force exerted by Mo in x direction, and force exerted by Larry in x direction, and force exerted by Curly in x direction. So which is equal to 80.5 newtons plus 80.5 newtons plus 80.5 newtons. So sigma Fx is equal to 241.5 newtons. Now simply we can find the acceleration in x direction, which is sigma Fx over mass, and it is 241.5 newtons over mass is 752 kilograms. So the acceleration is 0.321 meters per second square, and it is a positive value, therefore it's moving in the positive x direction. Now in part B, Larry and Curly push in the opposite direction to Mo's push. Therefore we can find the force values. Their force values are negative. So in part B, for Larry and for Curly, this is x. It is negative because they are pushing in the negative x direction. Now we can find the total force sigma Fx, which is equal to again force by Mo and the force exerted by Larry and the force exerted by Curly. Now in this case, the first one is positive 8.5 Newton and the next two are negative because they are pushing in the negative x direction. Therefore the answer is negative 80.5 Newton. Now to find the acceleration, we can use Newton's second law, sigma Fx over m. Now the force is negative value 80.5 Newton and mass is again 752 kilogram. Newton is simply the kg, ms minus 2, so the kilograms get cancelled, and we are getting a negative value for acceleration. Therefore the boat is moving in the negative x direction. Now let's see one more example before moving to the next section. A pitcher throws a 0.15 kilogram baseball, accelerating it from rest to a speed of about 90 miles per hour. Now we are asked to estimate the force exerted by the pitcher on the ball, assuming delta x equal 2.0 meters. So this is the picture of the problem. The pitcher is throwing the ball and we choose the x-axis to point in the direction of the pitch. And these are the known parameters: the mass of the ball, which is 0.15 kilogram, and the initial speed is 0 because it is starting from rest, and final speed is in 90 miles per hour. So the unit is miles per hour. So we have to convert the speed into SI units. So 1 miles per hour is equal to 1.5 miles per minute. By using that, we can find the final speed in meters per second. And the delta x is also given. And we have to find the force exerted by the pitcher on the ball, which is Fx in the x direction. Apply Newton's second law to find the force, but for that first we need to find the acceleration. For that we can use kinematic equation. Since we know the initial and final velocities, v0 and vf, and also we know delta x. Because of that we can use the equation involving these three terms, which is v square equals v0 square plus 2ax delta x. Here we know v0 and delta x, so we can find ax. So let's first isolate acceleration a from this equation. So v square minus v0 square is equal to 2ax delta x. Therefore ax is v square minus v0 square over 2 times delta x. Now we can substitute the values. V is 40 meters per second square minus v0 is 0, 2 times delta x is 2.0 meters. Therefore acceleration is 400 meters per second square. Now we know the mass, it is given, and we found the acceleration. Therefore we can simply use Newton's second law to find the force. So sigma Fx equal to mass times ax. Therefore this is equal to 0.15 kilogram times 400 meters per second square, which is equal to 60 Newton. Now in this section we learn about Newton's second law and to apply the equation for practical problems. For that, first we have to draw the free body diagram, and then we can easily apply Newton's law in the desired direction. So in the next section, let's discuss about Newton's third law of motion.